Okay, so for this final unit in the video, we're going to look at orbital properties. Essentially the properties of orbital motion. All right, so there's a couple things we're going to look at, so we're going to start first with just the movement. So let's just imagine we have a planet here. We'll for all of our references, we'll just use Earth as kind of our basis. So if I've got Earth and we're putting a mass in orbit around Earth, so whether this is a satellite or the moon, or it doesn't really matter. An object that orbits another object is referred to as a satellite. Okay, so again, if it's the moon is a satellite of Earth. The Earth is a satellite of the sun, and the sun is a satellite of the center of the Milky Way. And so anything that orbits another thing is considered a satellite. Now, whenever we do our orbital calculations, we assume that the orbits are circular. Now, that's a big assumption, and we'll get to that a little bit later. But for right now, all the orbits are circular. Okay, so what we're going to do first is we have to look at the type of forces that are involved for orbital motion. So for right now, you'll notice, well, the only force is gravity towards the center. So by Newton's second law, orbital motion is by Newton's second law, the net force would be the force of gravity. And since that's the only force, that would be equal to mass times the acceleration. And since it's moving in a circle, the acceleration would be centripetal. So if I put in my force for gravity, which we know is g, mass of the Earth, mass of the satellite, divided by the distance between the centers squared, that's going to equal the mass times the centripetal acceleration. Now, one of the first things you should notice is the two m's, which is the mass of the satellite, the little m. Since those are the same, that's going to cancel. And so what we're reduced to is that the gravity times the mass of the Earth over r squared, so how far our orbital distance is from the center, is equal to the centripetal acceleration, which itself is the tangential velocity squared over r. Well, algebraically, one of these r's are going to cancel, and then to undo the square on the velocity, we're going to take the square root. Okay, and we're left with this expression that v velocity is equal to the square root of the gravitational constant times the mass of the Earth divided by our orbital distance. And so this expression represents what we call the orbital speed of a satellite. Okay, it's a pretty defined equation. I don't think it's on your formula sheet. It's one you're going to have memorized, but it's not too bad. But the important thing to see is that the mass of the satellite did not affect the orbital speed of the satellite. So, and that's an important concept, is that no matter how big the satellite's mass is, it will not affect its orbital motion around the central mass. Okay, so one of the things that this equation tells us that's important is that if we consider the Earth again, and we put the satellite out here moving at a tangential orbital speed of v, okay, if v is less than the expression we found, well, then it's not moving fast enough to stay in orbit. So what will happen is it will lose the orbit at that orbital distance and will eventually spiral down, not necessarily into the Earth, because it's going to slow down to a point where it'll have a speed that, as the r decreases, it'll reach a point where that speed is enough to maintain that lower orbit. Okay? Now, at the same time, if we make v larger than that expression, then it's moving too fast to stay in that orbit, and it'll actually start to move outward from the center of or from the central mass, and eventually it'll get to a point far enough out that that speed will be enough to stabilize an orbit. So if it's going too fast, it'll just spiral outward until it finds a stable orbit. If it's going too slow, it'll spiral inward until it finds a stable orbit. Now, of course, if it's going extremely fast, then it'll just escape the orbital paths altogether and just fly off into space. And if it's going too slow for any of the orbital paths, then it'll just crash into the Earth. Okay, and so that's the importance for knowing what this expression for orbital speed means. Okay, so the next thing that I want us to look at is, let's return now to energy, and let's look at what the total mechanical energy is for an object that's in an orbit. Okay, so when we work this out, we basically would do, we would just do an energy problem, but we're not doing conservation of energy. Okay, it's not about figuring out what kinetic energy I had and how much I'll have after. This is just saying how much total kinetic and total potential do I have at this stable orbital distance. So the kinetic energy is half mv squared, and that's the mass of the satellite. And then the gravitational potential energy, which we just came up with, is the gravitational constant times the mass of Earth times the mass of the satellite divided by its orbital distance. Now all we want to do is add these together or combine these. So since we're in orbit, we know what the orbital speed should be. Okay, being that the satellite is in a stable orbit, we know that the expression for v is going to be what we just came up with, the square root of gravitational constant times the mass of the planet, in this case Earth, divided by the orbital distance. So if I plug that in for v, okay, and we do some of the algebra here, okay, what ends up happening is you get half of gravity, the gravity constant, times the mass of the Earth, times the mass of the satellite divided by r. But that expression is exactly the same as the gravitational potential, with a factor of a half in front of it. So this is actually an interesting result. Okay, so first, if I calculate the total energy, it's negative g times the mass of the planet times the mass of the satellite divided by 2r. Okay, this is the total mechanical energy that an object must have to be in orbit. But if you look at it, this is essentially the exact same thing as half of the gravitational potential. Okay, so this expression is your total energy for an orbiting object, and again, we're assuming a circular orbit. Okay, and again, you'll notice that that expression is half of the gravitational potential. Okay, so an object in circular orbits has a total potential or a total mechanical energy of half of whatever the gravitational potential energy is at that orbit. Okay, and so that also means that the kinetic energy is half of the potential energy as well. Okay, so again, if I want an object to go into orbit around a planet, it must have a kinetic energy equal to half of the potential energy at that distance in orbit. Okay, so the kinetic energy must be equal to half of the gravitational potential in order to maintain a circular orbit. Okay, so if we had a kinetic energy that was not equal to this, then the orbit is actually going to be elliptical. Okay, so one of the other things that I want to talk about in terms of energy is, if the total mechanical energy is that expression, why is it negative? Okay, so I've had some students ask, why is potential energy negative? And then when I calculate total mechanical, why is the total mechanical energy a negative number? Okay, and it's actually kind of a simple explanation. The idea is that if the mechanical energy is negative, that means that the object, in this case the satellite, is bounded to the central mass. Okay, so if you think about, if we took a ball and we threw it up in the air, and that had a, say, a positive total amount of energy, that means that the ball is escaping from the central mass, which in this case, for throwing a ball in the air, would be the Earth. Now, of course, we're not throwing it with enough velocity to actually get away, but if you think about the distance the ball starts at, when I throw it, it's getting further and further away from the center of the Earth, so that means it's escaping that distance, so it has a positive amount of energy. Okay, but if the total mechanical energy was negative, it means that it cannot move any further away than that location. Okay, so again, if the satellite had a positive mechanical energy, then the satellite would be escaping that orbit at that distance. Okay, so to understand that better, it would move out to a point infinitely far away, because at that point the gravitational force goes to zero and the potential energy also goes to zero when r is getting close to infinity. All right, so another orbital property I want to go over is the orbital period. Okay, so just like when we did circular motion, orbital period is essentially the time it takes for a satellite to complete one full orbit around its central mass. Okay, so to think about it, the Earth, as we know, goes around the Sun once every year, and so our orbital period would be 1 year, or 365 days. Okay, the Moon goes around the Earth every 29.5 days, and so those would be orbital periods. Okay, so let's look at how we calculate this. So you'll recall that orbital period was with a capital T, and if I wanted to just simply calculate period, or time, really, it's the distance divided by the velocity. Okay, so the velocity is the orbital velocity, which we found in the previous slides. Now the distance represents, it's not how far away we are in terms of the orbital radius. Remember, when we're going around in an orbit, the distance we travel is the circumference at that orbital radius. So we're going to put 2 pi r, because that's the circumference, out at some distance r. And the orbital speed at that location would be the square root of gravitational constant times the mass of the planet over the orbital distance r. Okay, so now if I work through this to do some basic calculations, okay, then I see that there's an r under the square root, and there's also an r in the numerator. So we can work through this algebraically and combine these r's. Okay, so the easiest way to kind of see that would be, I'm going to take that radical that's in the denominator, and when you're dividing by a fraction, you're really multiplying by its reciprocal. So if I rewrite this expression, that the orbital period t is equal to the circumference of the circle times the reciprocal, which would be the square root of r over gravitational constant times the mass of the planet. Okay, I can combine these r's if I just take this r on the outside and put it back into a square root. And so in order to do that, I would simply need to just square that r to put it inside of a square root. Okay, so now I've got an r squared times an r over gravitational constant and mass of the planet. So my final expression is going to be 2 pi times the square root of r cubed over the gravitational constant mass of the planet. Now, just like with orbital speed, one of the interesting things to take away from this is that the orbital period does not depend on the mass of the satellite. Okay, and the last thing we want to talk about is introducing a new scientist, and so this is Johannes Kepler, and we're going to discuss Kepler's laws, because one of the things that Kepler did created the laws of planetary motion. Okay, and the first law says that all orbiting bodies orbit in an ellipse. Okay, and it's an ellipse with the sun located at one of the focus points. Okay, now in comparison, so Earth, it is an elliptical orbit around the sun, but it's actually almost circular. In comparison with the other planets, it's a very circular orbit. Okay, but to compare it with something else, say something like Pluto, Pluto is an object that orbits in a very highly elliptical orbit. Okay, in fact, the period of Pluto takes over 200 years, Earth years. So it'll actually take longer than a few generations for Pluto to finally complete one orbit around the sun. Okay, now in the second law says that in an orbit, a satellite covers an equal amount of distance, or rather area, in an equal amount of time. Okay, so that's kind of confusing to understand, and it's better to see with a diagram. But the essential idea to this is that an object will move faster the closer it gets to the sun. Okay, so consider an example. So if I were to create a solar system in a way, just with one planet, so imagine we have a centralized mass, okay, which would be, the sun, and then further out you have, say, the Earth. Okay, so we've got this elliptical orbit, and so this is where the Earth is orbiting. If I pick any 2 points on the orbit, so we'll say these 2 points in green, and we look at the area that gets swept out by these 2 orbits. So if I imagine drawing a line from the sun out to the orbit of this planet, and I look at how the planet moves on this orbit, and it sweeps out this area in a certain amount of time. Okay, so we'll do this area in red. If I pick any other 2 points in the orbit and allow the same amount of time to elapse, okay, that planet will sweep out an exactly equal amount of area. So let's say if I go on the other side of the sun and I pick 2 new points and I look at the area swept out, we'll do this in a different color. But again, it's the same amount of time that took place. We get this area in yellow. Now, my picture is not perfectly to scale, but it turns out that those 2 areas are exactly the same. Okay, and this is really just an expression or a way to visualize a conservation of angular momentum. Okay, with the planet way out in orbit, further away, so if the r is bigger, it's going to be moving slower than if the object was more or was closer to the central star. Okay, so we can work this out kind of simply. If we look at the particle angular momentum, so the initial is r times mv, because this is the angular momentum of a particle. That angular momentum has to equal the angular momentum on the final side. Okay, so the m's are the same, so those are going to cancel out. And so all this basically shows us is that if the original radius is greater than the new radius, then the original speed must be slower than the new speed. So this is just conservation of angular momentum. Okay, so the final law, Kepler's third law, is probably the one we will use more often. Okay, and basically this law just simply states that for any planet, so I'm going to do this more visually. So here we've got, say, a centralized mass like the sun, and we've got 2 orbits, so 2 different planets orbiting the sun. Okay, if I look at how far away each planet is, so each has its own orbital radius, and each has its own orbital period around the same object. So both planets, say, orbiting the Sun, they have different orbital distances and different orbital periods. Okay, it turns out that if I were to look at the ratio of the square of the orbital periods over the orbital radius cubed, this ratio is the same for every planet that orbits the Sun. Okay, so the important thing for for Kepler's third law is that you recognize that this ratio is constant. Now, one of our learning objectives in AP Physics C is that you have to be able to use Newton's laws to verify Kepler's third law. Okay, so what we're going to do then is use Newton's law to prove that this ratio of t squared to r cubed is in fact a constant for anything that orbits the same central mass. Okay, so let's do that on a new slide. Okay, so we're going to start, we've already proved this. If you go back to when we proved how to find orbital speed, and then, with orbital speed we could get orbital period, it all started with Newton's second law, with gravitational force is equal to the mass times the centripetal acceleration. So that's what we're going to do now. We're going to, rather than starting back at step 0, let's skip ahead to where we develop the equation for the period. Okay, so if we write out the period equation, that it's 2 pi square root of the orbital radius cubed over the gravitational constant times the mass, and in this case we'll say it's the mass of the Sun, because we're talking about this is the orbital period of a planet. Okay, so one of the interesting things is you'll notice that there's nowhere in this orbital period equation that identifies the planet except for whatever the orbital period is and whatever the orbital radius is. Okay, so if I take those two numbers, the orbital period and the orbital radius, and put them on the same side of the equal sign, okay, and we're going to do that because those are the two properties that are dependent on the planet that's in orbit. Okay, so the orbital period, if I square both sides, the 2 pi becomes 4 pi squared, but it gets rid of the radical. So now I have r cubed over gravitational constant times the mass of the Sun. Now if I divide out the r cubed to both sides, that gets rid of it on the right side. And then on the left side, I have the ratio I wanted, which was period squared divided by the orbital radius cubed, is equal to 4 pi squared over gravitational constant times the mass of the Sun. Well, everything on the right side is a constant. The 4, the pi, the gravitational constant, and the mass of the Sun. All of these numbers are constant for any planet orbiting the Sun. That means that the square of the orbital period and the cube of the orbital radius, that ratio is in fact constant for any planet that orbits the same central mass. Okay, and so that is using Newton's laws to get Kepler's third law.